So now we will start with the another topic that is very important in thermodynamics, that is properties of pure substance. Now we will talk about properties of pure substances. So first of all, I would like to describe what is the meaning of pure substance. So first of all, I will define what is the meaning of pure substance. So pure substance is a substance of constant chemical composition throughout its mass. So we can write for pure substance, a pure substance, a pure substance is a substance of constant chemical composition, constant chemical composition, chemical composition throughout its mass, throughout its mass. Again, I will define a pure substance is a substance of constant chemical composition throughout its mass. It is a one component system. It is a one component system. It may exist in one or more phases. It is exist in one or more phases. So that is a pure definition of a pure substance. So sometimes the people are saying pure substances only exist in one phase, but it's not like that. Pure substance is a substance of constant chemical composition throughout its mass. Although it is a one component system, but it may exist in one or more than one phases. So I am giving some examples of pure substance. For pure substance, we can take atmospheric air. So atmospheric air we can take steam water mixture, steam water mixture. The steam water mixture we can consider as a pure substance, and the combustion products of and combustion products of fuel. So these are the some examples like atmospheric air, steam water mixture, combustion product of a fuel. All these are the example of pure substance, because in all the examples, like if I consider atmospheric air or if I consider steam water mixture, so in steam water mixture the chemical composition will remain same throughout the mass. But if I take an example of air and liquid air, suppose I am taking an example of air plus liquid air. So for our understanding, we should be clear, like in air and liquid air, we should not call it a pure substance. So air plus liquid air is not a pure substance. It's not a pure substance. So keep this thing in mind. The air plus liquid air is not a pure substance. The reason is because the relative proportion of oxygen and nitrogen differ in gas and liquid phase. So the question comes, why air plus liquid air is not a pure substance? So the answer is the relative proportions of oxygen and nitrogen differ in gas and liquid phase. Gas and liquid phase. So this is the main reason why air plus liquid air is not a pure substance. So now I think it is clear about pure substance and what should be the main property of pure substance, that is constant chemical composition throughout the mass. A point comes in our mind, how many properties are required to define a pure substance. That is very important because in this chapter we are basically interested in properties of pure substance. So we have already defined the definition of pure substance. Now we are interested in how many properties are required to define a pure substance. So basically in majority of cases a minimum of two properties are required to define the state of a system. If you know, like if suppose I am talking about any gas, so I will talk about pressure and I will talk about volume. So I'm talking about these two properties, that is pressure and volume. And if you see, one, pressure is a intensive property and volume is the extensive property. So what is the general rule? So we can say that in majority of cases, minimum of two properties are required to define the state of the system, in which the one will be the extensive property and second one will be the intensive property. So I am writing here, in a majority of cases, in a majority of cases, a minimum of a minimum of two properties, a minimum of two properties are are required to define the state of a system. State of a system. The best choice is the best choice is an extensive property. Extensive property we have already defined, which is depending on mass like volume, energy. And one should be intensive property. Intensive property. The properties which are independent of the mass. So this is a very general rule for defining the state of the system. We require two properties. One should be the extensive property and second should be the intensive property. So sometimes uh, if we take in case of saturated liquid, saturated vapor, or pure substance having two phase, three phase, so sometimes we confuse, like basically how many properties are required, because whatever I told right now, that is two property, that is a general. Sometimes we require only one property, sometimes we require only two properties, sometimes we don't require any properties to define. So now I will tell there is one rule which tells how many properties are required to defining a state of a system. So there is one rule called Gibbs phase rule. So now I will talk about Gibbs phase rule. Gibbs phase rule. So Gibbs phase rule is basically for determining the number of properties is required for defining the system. So Gibbs phase rule generally for defining degree of freedom, we can say that. Degree of freedom. Degree of freedom is nothing but properties. How many properties are required for defining a system with the help of Gibbs phase rule. So I will now just write the Gibbs phase rule. That is F equals to C minus P plus 2. Here F is number of degrees of freedom. Number of degrees of freedom. Or we can say that number of independent properties. Independent properties. Second one, P, that is number of phases. Number of phases. And C is nothing but number of components. Number of components. Means if we know the number of components, if we know the number of phases, then definitely we can easily calculate the number of degrees of freedom, or in other words, the number of independent properties required for defining the system. So with the help of Gibbs phase rule, we can easily find out the number of independent properties required for defining the system. In writing the Gibbs phase rule, that is F equals to C minus P plus 2, I will take different case. Suppose I am taking case first, that is single component, or we can say that pure substance, because pure substance is single component system. Pure substance, single component, single phase. So for this case, we will find how many properties are required. So here, single component means C equals to 1, single phase means P equals to 1. So if I plug here F equals to C minus P plus 2, if I plug here P1, P1, P, F equals to 2. So I can say that two properties are required. Two properties are required. Similarly, I am considering the second case, that is case 2. Single component, two-phase system. Two-phase system. So now single component to C is 1, phase 2, P equals to 2. If I use the Gibbs phase rule, that is F equals to C minus P plus 2, so F equals to C 1, P is 1 is 2, P is 2. So here I will get 1. So one property is required. Similarly, I am considering the case 3. Case 3, that is single component, three phase. So I will mention here one very good point. Whenever there is a single component and three phase exist in equilibrium, this point is called triple point. Means I will define one term before using the Gibbs phase rule, that is triple point. Triple point is a point where all three phases will be in equilibrium. So for this thing, I can say a triple point. So now if I apply this thing, we know component is 1, phase is 3, and if I use the Gibbs phase rule, F equals to C minus P plus 2. For C I will write 1, for P I will write 3, so F will be 0. No property. Is required. So we can say that for single component 3 phase or a triple point I will again mention is a point where all three phases are in equilibrium. There is no requirement of any property for defining the system. So various kinds of diagrams for our clear understanding of the state of the substance, where at which position the state of the system is lying. So here I am just taking the diagram one by one. So first of all, I am taking TS diagram. So first I will take TS diagram. So TS diagram is nothing but temperature entropy diagram. So here I will draw the temperature entropy diagram. On y-axis I will consider the temperature, and on x-axis I will consider the entropy. So now I will draw one dome here like that. So by this way we can clearly understand various phase of substance. So here if you see from suppose point A here to that is point C, and let's take this is point B. If we see in A to C, the state of the substance is full liquid. So from A to C, we can say that it's a liquid phase. So we can say that saturated liquid. Saturated liquid. Similarly, if we go from C to B here in this line, we can say that it's a pure vapor phase. So we can say that it's a saturated vapor. And in between means under the dome. Suppose I am here. Suppose at a state 1. So it's a mixture of liquid and vapor. Liquid plus vapor. So here in under the dome, if you see this region, here we are getting a mixture of liquid and vapor. On this line we are having only the liquid. On this line we are having only the vapor. If you see here also we are having the liquid zone. Here we are having the vapor zone. Here I can say that is liquid zone. Here I can say that it's a vapor zone. Now it's clear for identifying where I will get pure liquid, where I will get pure vapor, where I will get the mixture of liquid and vapor. So I am just showing the various phases and the mixture of phases on TS diagram. So in TS diagram, I will tell one more thing: constant temperature lines. These are the constant temperature lines you can easily see. These are the constant temperature lines. So here temperature is constant, temperature is constant, temperature is constant. And if we know how to draw the constant temperature line, so easily we can draw the TS diagram and easily we can point the real state of the system very clearly. So for drawing the diagram is always better if you identify the state of the system clearly. Another diagram, that is enthalpy entropy diagram. Remember, sometimes enthalpy entropy diagram is called Mollier diagram. So I will just draw the enthalpy entropy diagram. Similarly, I will show the enthalpy on y-axis, that is enthalpy entropy on the x-axis, and here we are having this kind of dome. So we can easily understand in that dome here. This one is the saturated liquid, saturated vapor, and in between we are having the mixture of that. Now I will draw the constant pressure lines here. So these are the constant pressure lines. Similarly, I can draw the constant temperature lines also. So this is the constant pressure, this is constant temperature. So here P equals to constant, P equals to constant, here T equals to constant, here P equals to constant, T equals to constant, P equals to constant, T equals to constant. So this is the clear representation of the enthalpy entropy diagram, that is pressure volume diagram. So similarly, I will take pressure on the y-axis and volume on the x-axis, and this one is the shape of the diagram here. And now on this diagram I would like to draw constant temperature lines. These are the constant temperature lines. So I can say that this one is T equals to constant, T equals to constant. This is the clear representation of the PV diagram. So by this way we can easily understand the uh, behavior of pressure volume diagram, the triple point. So there is one important point called critical point. So critical point is very important in uh, understanding the state of the pure substance. So critical point is a point above which a liquid upon heating suddenly flashes into vapor, or a vapor upon cooling suddenly condenses into the liquid. So I will write above critical point, critical point or liquid upon heating suddenly flashes into vapor, or a vapor upon cooling suddenly condenses into liquid. I will again repeat above critical point. A liquid upon heating suddenly flashes into vapor, or a vapor upon cooling suddenly condenses into liquid. Means there is no distinct transition zone from liquid to vapor and vice versa. So I will write there is no distinct transition zone from liquid to vapor, from liquid to vapor, and vice versa, and vice versa. So now by TS diagram I will show triple form TS diagram. So we know we have already discussed about TS diagram. If we suppose consider a state here 1, and if we are consider a second state here 2, we know 1 is saturated liquid, 2 is saturated vapor, and here if you go from 1 to 2, so here we are having a mixture of liquid plus vapor. Means here what is happening here, the latent heat is taking place because we are converting the liquid into vapor. So latent heat is taking place here. And now if you go up and up, suppose I am here now from 1 dash to 2 dash. Here I am taking more latent heat. Here I will take less latent heat. Similarly, if I move from 1 double dash to 2 double dash, latent heat will be less. And if I come here where the 1 triple dash is coincide with 2 triple dash, there is no need of any latent heat. Means the liquid directly converted into vapor, or vapor upon cooling suddenly converted into liquid. So that is called triple point. No, critical point, sorry. Critical point. So one more special thing, at critical point, specific heat at constant pressure is infinite. So I can say at critical point, specific heat, specific heat at constant pressure is infinite. Infinite. Talk about quality of steam or dryness fraction. I will talk about quality of steam generally, or dryness fraction. Dryness fraction. So let's talk about in terms of TS diagram. I'm again drawing the TS diagram. So it's TS diagram. I'm taking one state 1, I'm taking 2, I'm taking here 3. If suppose 1, what is 1? That is saturated liquid. So here there is nothing like dryness. So here the dryness fraction or quality of steam will be 0. So I can say that dryness fraction 0. Similarly for 2, here I am having saturated vapor. So saturated vapor, there is nothing like liquid particles. So it is full dry. So I can say that dryness fraction is 1. And for 3, dryness fraction will lies between 0 to 1 because third stage is in between 1 and 2. So the dryness fraction third stage it will be between 0 to 1. So now I will define the dryness fraction. It is nothing but the mass fraction of vapor in a liquid vapor mixture. So I will define dryness fraction or quality of steam. Quality of steam is mass fraction of vapor in a liquid vapor mixture. Vapor mixture. So I will write dryness fraction is denoted by X. mv is mass of vapor. mv plus mf, or we can say that ml. That is mass of liquid plus mass of vapor, or we can say that liquid vapor mixture mass. So dryness fraction we can calculate with the help of this formula. Some of the formulas with respect to wet steam and superheated steam. So first I am considering the wet steam. So again I will talk about in terms of TS diagram. You can also talk about in terms of PV or HS diagram. I am just talking about in terms of TS diagram. So here we are having same the state 1, here we are having the state 2, and here we are having the state 3. You see 1, the 1 is we are having the saturated liquid, 2 is saturated vapor, and 3 is the mixture of liquid plus vapor, which is having a dryness fraction S. Suppose dryness fraction X. And we know we will denote the saturated liquid properties by F and saturated vapor property by G. So now here we are having a mixture. So the properties of mixture, properties of liquid vapor mixture. Suppose I have to find out the specific volume of mixture V. So we know the specific volume of liquid, we know the dryness fraction, and we know the specific volume of gas, and we also know specific volume of liquid. So by this way we can easily calculate the specific volume of mixture. Sometimes we are also using V equals to Vf plus X VGF. So VGF is nothing but Vg minus Vp. Similarly, if suppose we want to calculate the enthalpy H, so we can write HF plus XHG. So by this way we can calculate the enthalpy. Similarly, we can also calculate the entropy. S is nothing but SF is X S G. So by this way we can calculate the entropy of the mixture. Similarly, we are having sometimes superheated steam. We are having superheated steam. Superheated steam means here we are having steam at point 2 that is saturated. If we go in that zone, suppose at point 4 we are having saturated steam. Similarly, if suppose we are here at point 1 and if we go here at point 5 we are having subcooled liquid. Here we are having superheated steam. So I can write point 5 is subcooled liquid because we are cooling the liquid from saturation state. Similarly, this is called superheated steam because we are already having the vapor. I am calling it steam at saturated vapor at a point 2, but here we are heating, so we are having in a superheated state, that is called superheated steam. So for superheated steam we can again calculate the properties of the steam. Here how we can calculate H for enthalpy, we can calculate Hg plus Cp T superheat minus T saturated. I am taking here Cp, specific heat at constant pressure, because this one is a constant pressure process. Here I can write, because we have already seen these kind of lines is showing pressure equals to constant. So I can put P equals to C here. Similarly, we can calculate the entropy also, that is entropy of gas plus Cp log of T superheated by T saturated. So by this way we can calculate the entropy also. So these are the formulas related to the superheated steam.